All right, we should get started here. I'm a couple minutes late. Small class today also. With Jeff gone, I had to set up the camera, which was harder than I thought. So kudos to him for doing it the whole semester. This is our last lecture that I'm going to give on advanced topics. And then next week, I think it's just going to be Kevin and Shiva each giving one lecture. Is that what you guys decided? And yeah, so Wuyang will give her advanced topic on MCMC during the recitation that week. So there's some fun stuff coming up next week, some interesting advanced topics. So last time we talked about coordinate descent, and I gave the intro to that topic as it's something that statisticians and people who do machine learning care about, but you might not see it in an optimization context, or at least not emphasized as much. And today is another one of those topics. So we're going to talk about path algorithms, which is, again, something that people in optimization tend not to think about as much, but people who do statistics and machine learning do. So another nice kind of special topic, especially because this is an ML course. Are there questions about coordinate descent from last time before I go on to path algorithms? People have any questions about that? Okay. So in this lecture, we're going to be talking about problems of this pretty general form, where we have minimize over all x, g of x plus lambda times h of x. And lambda here is some non-negative real number. And we're going to assume that g and h are convex. Usually it turns out that g is differentiable, but this is just a pretty general form. And you can immediately see that a lot of the problems we've visited so far fit into this framework. We usually call lambda here the tuning parameter in a problem of this form because it has kind of a statistical meaning, which you'll see as we talk about the problems, why it's called the tuning parameter. But we're going to look at what's called path algorithms. So these are algorithms that deliver not the solution at a fixed lambda, but actually delivers the solution as a function of lambda. So we're going to aim to get this entire set, the set of all x star of lambda, such that lambda is between 0 and infinity. So 0 meaning that we're just minimizing g, and infinity meaning that we're essentially minimizing h, and g has no consequence. Okay, so it describes the trade-off between minimizing g and h. It's another way of thinking about the tuning parameter broadly. Okay, so path algorithms usually start at one end of the path, so either at lambda equals 0 or lambda equals infinity, depending on what's easier. And then we trace out the solution as a function of lambda by kind of iteratively or recursively or successively satisfying the KKT conditions. So that's a very general way of describing it, but that's the basic idea. We write down the KKT conditions and we think about how they evolve as lambda changes. And we try to solve them continuously as lambda evolves, not for a fixed lambda. So what are the properties of path algorithms? One of the unique properties of path algorithms is that they deliver the exact solution. So when we're talking about path algorithms, kind of in a strict sense, where all the examples you'll see today, they deliver the exact solution at all values of lambda. So there's no iteration here. It's not like a first order method where we're going to iterate and then we're going to get some kind of error bound, like after k iterations we're 1 over k away from the optimum in terms of the function value. Or we had the same guarantees with Newton's method. We had guarantees with the interior point methods. We didn't really talk about those guarantees for the dual methods, but they exist also. This is very different. There's no iteration here, in the sense that we're not iterating kind of to get closer and closer to the solution. And there's no error-bound guarantees. We're guaranteed the exact solution for all values of lambda. And they also provide a useful platform for selecting this parameter, lambda, from the perspective of a statistical problem or a machine learning problem. So that's really why people care about them in statistics and machine learning, is for the second reason. The first reason is actually it also can be important. Sometimes even iterative methods, if the problem has a very special structure, aren't desirable if they're giving you approximate solutions. But I'm not really going to talk about this first property today. Today we'll talk about path algorithms, and we'll also talk about the second property. Okay, any questions about that? Okay. Before I go into this example, actually, I want to kind of mention one thing, which is that path algorithms, they're not applicable to you can't drive a path algorithm for any particular problem, right? If I'm telling you that in general I can tell you the exact solution for all values of lambda, then there'd be no reason to even study other methods, really. So it's like coordinate descent, in which, when applicable, it can be very useful, and it can be a great thing to have in the toolbox. But also, like coordinate descent, it does not apply broadly to every problem, which is why these other methods, like first-order methods or the interior point methods or Newton's method, etc., that's why we also care about those, because they apply a lot more broadly. Okay, so we're looking at a more special class of problems, and we can do a little more specialized, we can derive a little more specialized algorithms because of that. Okay, so this is the example that we're going to derive a path algorithm for, and we're going to do this in detail so that you can get a flavor of what path algorithms look like, or what a particular path algorithm looks like. Because this one is a pretty natural problem in order to look at the path. So in this problem, we're going to be considering 1D total variation denoising, or the 1D fused lasso, so they're kind of synonymous, in which we observe y, and let's suppose we observe y at locations 1 through n that are ordered successively. Okay, so here's 1 through 100, and I just suppose that I observed y to be these dots. Okay, so at each position along this equally spaced grid of length 100, I observed a y value. Okay, so the 1D total variation denoising problem tries to denoise those y values by fitting a piecewise constant signal to them. Okay, so what does that mean in terms of the optimization problem? It means that we have two terms. The first term, I don't know why I put a beta there. I think it's because I usually think in terms of beta, like most statisticians do. But the first term should say y minus xi squared. So the optimization variable is x. So we're looking at minimizing the following criterion, yi minus xi squared. So let's keep our estimates close to y, plus lambda times the differences in the absolute value. So the absolute value of the differences between adjacent coordinates of x. Okay, so I take x1, I subtract off x2, take that in absolute value, I add on the absolute value of x2 minus x3, the absolute value of x3 minus x4, etc. Okay, and lambda here, it controls the importance of these two terms, the relative importance. So if lambda was 0, what would the solution be? It should be xi equals yi for every I. Okay, so our red line here would just be joining all of these points. That would be the solution. When lambda is large, what happens is that this penalty forces coordinates of the solution that are adjacent to be equal. So for a really large lambda, we're really putting a lot of weight on the fact that the solution is different from one of its neighbors in a particular coordinate. So it forces coordinates to be equal, and that's why we get this piecewise constant structure. So here I took this example. I chose lambda equals 5, and the solution here, which is really a discrete vector, just like y is, right? I really only get one xi value for every location along this this grid, but I just drew a line through them to kind of emphasize their structure. It's equal in the first, like, maybe 22 components because of this term, and then it chooses to make a breakpoint between somewhere around the 20th point and the 21st coordinate, and then we have this another flat stretch, another flat stretch, so we have, looks like 5 flat stretches total. Okay, so we've accomplished our goal of fitting a piecewise constant function. Other questions about the setup? Because it's important to understand at least what the problem is doing before we talk about the path algorithm. Okay, so here's a much smaller example. I just took 10 points here, and I showed you the solution for 6 different values of lambda. And actually, I showed you the solution exactly at the points at which 2 neighboring components of the solution are joined together. So we actually call that, hence the name, we call that fusing. So I'm showing you 6 different values of lambda, which 2 neighboring components of x are fused. Okay, so it starts off that at lambda equals 0, the solution is just equal to yi in every component. And then when you increase lambda a little bit, we join these 2 coordinates together at the solution, which is not surprising, right? Because they are the ones that are closest. So you'd expect those to be the ones that are fused first. Okay, then I increase lambda some more, and the next 2 things that fuse are actually these 2 coordinates. Okay, you can see that their values, in terms of the x value, is the same. And then increase x some more, and then these 2 components fuse. And then at some point, these 2 components fuse. And then at some point, these 2 components fuse. And finally, at the left, I'm going to fuse this group with that group. So I'm fusing a group of coordinates of size 2 with a group of coordinates of size 2. So this was just kind of like the evolution of the structure in the solution. Okay, I'm telling you, it's not obvious why, but I'm telling you that in between these 2 lambda values, there were no fusions. Okay, so I'm just showing these lambda values because they're of interest. So the strategy for our path algorithm is to construct a sequence of lambda values at which these fusions occur. So we're going to actually seek out directly the values of lambda at which the 2 components of the solution become fused. And this is a nice algorithm that's taken from this paper by Heffling in 2009. So moreover than that, we're also going to show that in between these critical values, so in between these values of lambda at which the solution, the components of the solution fuses, the solution is simply linear as a function of lambda. So if I told you I knew the solution at lambda equals 0.1 and the solution at lambda equals 0.299, and you wanted the solution somewhere in between, say lambda equals 0.2, then I could just linearly interpolate each coordinate of the solution between here and here. So once we find these critical values, we've actually found the entire path, right? Because now any value of lambda is going to lie between one of those 2 critical values, and we can find the solution exactly just by linearly interpolating. So just in terms of a little more explicit, in terms of the math, if I tell you that I want a solution at a value of lambda, then we just go look up which critical values does this lambda lie in the interval between those 2 critical values. And then we just take a convex combination of the solution at lambda k and lambda k plus 1, right, where the weights just reflect how far lambda is along in the interval between the 2 endpoints. So before we start the algorithm, one important thing to ask is how many critical values are there? Right, if I'm running the algorithm and I told you that there's a possibility for there to be infinitely many critical values, that would be a problem. So in particular, how is it possible for there to be more than n-1 critical values? Think about each critical value I said corresponds to the fusing of 2 components. So how could we have more than n-1? Is there a situation in which you could imagine there's actually more than n-1? What's that? Change. So you mean as I increase lambda, 2 things actually separate? Yeah. So that is a way for it to happen. So, for example, if I increase lambda in a group that was of size 5, all of a sudden split into a group of size 2 and 3, then I have to join them again at some point. Right? Because I should also mention that we know that when lambda is infinity, everything's in one group. Right? Because everything here is being forced to be equal to its neighbor, so the solution at infinity is just going to be a single red line. So we know that at the biggest lambda value possible, they're all going to be in one group. So if for some reason things actually split up as we increase lambda, then we'd have more than n-1 critical values. Okay, but that seems a little bit weird if you look at this problem. It seems like as we increase the importance on being close to your neighbors, we should not have the behavior that something that was fused at a smaller value of lambda becomes unfused later. That would seem just kind of be contradictory at an intuitive level when you look at the criterion. Okay, so sure enough, you can actually show that's true for this problem. So this is one place in which this result occurred, but you can find it and you can prove it in other ways too. So the way that we're going to say it just explicitly is that if I give you any coordinate of the fused lasso solution, and I look at that coordinate as a function of lambda, if it happens to be equal to one of its neighbors at some value of lambda, then at all values of lambda larger than that, so at all lambda prime, it's still going to be equal to its neighbor. So in other words, once groups of coordinates fuse, they're never going to unfuse or split apart as we increase lambda. Okay, so that tells us that there are exactly n minus 1 critical points.
It could be less.
Yeah, you're right. So it could happen that I end up fusing two things exactly at the same value of lambda. We could also consider that a critical value, or two critical values just at the same point. So that's a good point. Okay, so there's at most n minus 1 critical points, and depending on how we define them, there's exactly that many too. Okay, so is it clear what our objective is? We're just going to find these lambda values, and also in find them, we're going to prove that in between those lambda values, the solution is actually just linear as a function of lambda. And once we do that, we'll have found the path. Is this algorithm only applicable to this problem? Is that what you're asking? Right. Is it true that this... Yeah, so we're just kind of studying this as a case study to begin with, and then we'll talk about what properties of this particular example carry over to more general cases. But it is important to keep in the back of your mind what allowed us to be successful in this case in terms of driving the path algorithm. And we'll talk about that in detail after we talk about this example. Okay, so here's our problem. And the KKT conditions should be pretty natural at this point for you to derive, considering we've done this many times, but we're going to go through them anyways. Okay, so our problem is to minimize this over x. Okay, and the KKT conditions look like this. So the first term, it's differentiable, right? So I just take its gradient, and the ith component of its gradient looks like this, xi minus yi plus lambda times the subgradient of the infinity norm of the difference between xi and xi minus 1, or I guess this is a plus 1. I want to be careful that I don't mess up the indexing. So, I mean, we can think about it in a couple ways, but one way is just to use the chain rule of subgradients, right? And that ends up giving us a term si, which is the subgradient of this term. And we also have a term si minus 1, because we also have a term in the sum that looks like xi minus 1 minus xi. Right? So xi appeared in two of those absolute values, so I had to account for it in both places. This has to be equal to 0 for I equals 1 through n, where si is the subgradient of the absolute value function evaluated at xi minus xi plus 1. Okay, and just for convention here, I'm going to take S0 and Sn to be equal to 0, and that's going to be helps me just write this without having to do cases. Okay, so these are the KKT conditions, and we know that if we can find an x that satisfies this, and a subgradient of x that satisfies this, then we have the solution. So we're going to kind of study the evolution of these equations as lambda changes. So lambda equals 0. Right, we know the solution, x star of 0, is just equal to y. Okay, we can see that, for example, just by looking at the problem up here. It's obvious that we just would take x equal to y. Okay, now for a really small value of lambda, let's consider taking the following as our proposed solution. So in the ith coordinate of x, I'm going to let it equal yi minus lambda times the sine of yi minus yi plus 1 minus the sine of yi minus 1 minus yi. Okay, so I've actually written this down as x star, but At this point, we don't know it's the solution. We're just proposing this as a potential solution for a really small value of lambda. So now the thing is to check that this satisfies the KKT conditions, and if we've done that, then we know it indeed is a solution at lambda. Okay, so let's plug that in. We get xi star minus yi plus lambda si minus si minus 1. Okay, so the yi here cancels with that one, and we end up getting lambda times si minus the sine of yi minus yi plus 1. Then this term we end up getting minus si minus 1 minus the sine of yi minus 1 minus yi. Okay, so that's what we have left over. So if we could take si equal to this sign and si minus 1 equal to that sign, then this whole thing would be 0. Right, that would be true if we could take these to be equal to each other. Okay, but now the question is that a valid subgradient of x? Right, because we can't just take s to whatever we want. It has to be actually a subgradient of x. In other words, we have to know that the sign of xi star lambda minus xi plus 1 star lambda equals the sine of yi minus yi plus 1 for any I. Okay, so if this was true, then do we all agree that I can actually take that to be the subgradient and we'd have the solution? People confused about that, or is that clear? Nod your head if it's clear. Okay. So, does anybody think this is obviously true? That this fact is true for a small lambda? And if you do, why do you think it's true? What's that? Can we change the sign? That's interesting. I'm not sure that will kind of carry through. Let's draw it, because I think it's actually easier if you see a picture of it. So like these are the y values, right? y1 through y4. And I started off with x the solution at lambda equals 0 being defined to be just yi. So at lambda equals 0, these are the y values, and those are also the solutions. And then how do we define x as a function of lambda? Well, as a function of lambda, it was up here, right? But if we look at that as a function of lambda, it's really just ai minus lambda times bi. Just a linear function of lambda, right? Here's ai, and here's bi. So we're taking these x's and we're deforming them continuously by this linear transformation. So for a very small value of lambda, if the x's started here and I apply a linear transformation to them, they should all be on the same side of each other as they were initially, right? So the x's are here. I apply some transformation to them, so they either move up or down. But for a small enough value of lambda, right, I'm not going to get a switch in the ordering of them. Because in the very worst case, this guy moved down and this guy moved up, but if lambda is small enough, I can control how far they're going to move. So they're going to have the same signs in terms of the adjacent differences as the yi's will. So certainly for a small enough value of lambda, I can certainly say this is true, and then I have the solution, just at this value of x. Okay, so here's another way of looking at that. I've actually drawn here, for this example that we had, this one here, I've drawn x on the y-axis, the value of x on the y-axis, and the value of lambda on the x-axis. So lambda equals 0. Each point here, each coordinate of x was just equal to y, And then as I increase lambda, I told you, right, each of these is a linear function of lambda. So here's what that linear function looks like for each coordinate. Here's x. This one, for example, is, I think, the fourth component of x is a function of lambda. Each one of these is a different component. And what we have said, what we proposed in the previous page, is a valid solution unless two of these lines cross. Because when two of those lines cross, then that sign condition is wrong. Right? It's no longer true that xi minus its neighbor is equal to the sign of yi and its neighbor, because they flip signs. So from lambda equals 0 all the way up until they cross, which is some value, which is going to be positive because just by continuity, right? They're different at 0, so as I increase lambda, they're going to be different for at least some small region. I have the solution exactly that I've written down for you. So what's the value at which they cross? Well, that's at which one of them crosses. That's pretty easy. We just have to say when is ai minus bi lambda equal to ai plus 1 minus bi lambda, bi plus 1 lambda. Okay, what value of lambda does that occur? And when we solve for lambda, we get ai minus ai plus 1 all over bi minus bi plus 1. Okay, so that's when, for example, paths I and I plus 1 cross. So if we're looking for the smallest value of lambda at which any two paths cross, I just take the minimum over all I of ai minus ai plus 1 all over bi minus bi plus 1. So in the picture, that's just this dotted line. I can stretch out lambda and see when any of these two paths cross, and I just found the first time right there. So this is what we define as the first critical value. And so far we've done exactly what we proposed to do. Right? We've found a value of lambda which two of the groups fuse. This is when two of the components of x are equal. And we've proved that between 0 and this critical value, the solution is a linear function of lambda. Okay, so far we're good. And we've exactly computed the path for all lambda between 0 and lambda 1, where lambda 1 is defined up here. Okay, but now if that was all we had for a path algorithm, it wouldn't be very useful, right? Because we say, well, we can solve it for all lambda in some region. That region could be very small. So the point is we have to kind of repeat this argument. And that's the idea behind the path algorithm. So now we're going to invoke our lemma, this lemma that we learned. Coordinates 4 and 5, which are these top two coordinates here in the picture, it looks like it's maybe green and light blue, but they're very similar colored. Because they were fused at this value of lambda 1, we know from our lemma that they're never going to unfuse for bigger values of lambda. They're going to be the same. So actually I can go back to my optimization problem, and I can define groups of coordinates. Now the first group just contains the first coordinate, the second and the third the same. The fourth group contains, say, the fourth and the fifth coordinates together, because I know they're going to be fused, and so forth. And all I'm doing now in rewriting the problem is that I'm saying that I'm going to solve it using only one variable for the fourth and fifth component of x. So I know that they're going to be the same for all larger values of lambda, so let me just rewrite the problem to reflect that. So that's what I've done here so far. Okay, it may look a little bit more complicated, but that's all I'm doing. I'm encoding in the criterion the fact that x4 and x5 are the same variable. So this is how I rewrite the problem. I plug in a common value for x4 and x5. I can redrive the KKT conditions. Okay, so all that does here is that I get a very similar set of KKT conditions, except for I'm just reflecting the fact that I have groups now. So let me write down the problem here first so you can see how it follows. So now I have here, the problem, I have this sum over all I and the sum over all j that are in the ith group of coordinates of yj minus x gi. So I have one common optimization variable for every component of the group. Because by that lemma we know that for larger values of lambda, that's going to be true. They're going to be all the same. at the solution, plus lambda times, now the difference is going to be taken across adjacent groups. Okay, so if I derive the KKT conditions for this problem, if I take the, for example, with respect to the g-ith component of x, or the ith component of this xg vector, then I get one xgi for every term in the sum, and this is just the cardinality of gi, the number of terms in that sum, minus I get a value of yj from every term in that sum, so that's where that comes from, plus the same thing as before, two subgradients, one for this term and also one for the term that looks like xgi minus 1 minus xgi. Okay, so it's completely analogous to what we had for the case where we had each variable being its own group, except for we have the number of groups here and a sum over y and the sum over the elements of y over the elements of the group. Okay, so now we know that by construction, we know that the vector that we just wrote down at lambda 1 satisfies these KKT conditions, because we solved the problem from all lambda from 0 all the way up to lambda 1. Okay, so now for a larger value of lambda, for some lambda that's bigger than lambda 1, we're going to again try to proceed in a linear direction from the solution. Okay, and now what am I going to choose for AI and BI? Well, I have the formulae down here on the paper, but it's really very simple. We just look at the KKT conditions, and we kind of reverse engineer what AI and BI should be so that they're set equal to 0. That's all I'm doing. Okay, so I want to plug this into KKT conditions, so I get GI times AI minus BI lambda minus the sum of all the yj's, j in that group, plus lambda times the difference of subgradients. Actually, this should be an I minus 1. And now I'm just choosing AI and BI so that this is 0. Okay, so for AI, I'm going to try to cancel out all the terms that don't involve lambda, right? Because I have to, because the ones that involve lambda, if they're going to be equal to 0 for evolving lambda, I need to make their coefficient 0. So for AI, I'm going to cancel out all the terms that don't involve lambda, such as this term and this term right here. So I choose AI to be equal to the average value of y in the group. That's it. And for BI, I'm going to choose that just to be equal to this right here. Okay, but in particular, I'm going to choose it to be equal to these subgradients at lambda 1, because then I know that I satisfy it at lambda 1. So we're going to choose it to be equal to the, again, I have to divide by GI, the difference in the sign of the solution at lambda 1, which we have access to, right, because we just solved all the way up through lambda 1. This should say I plus 1. And now the same thing, but just one coordinate earlier. Oops. So as long as I can take this subgradient equal to this sign and this subgradient equal to that sign, I've made the KKT conditions equal to 0. So it's the same story we played at the start, which is, when is that a valid subgradient? When is it okay for me to say that at some value of lambda, the signs and the adjacent differences of this vector are the signs and the adjacent differences of our solution at lambda 1? Because if those signs are the same, then we've satisfied the KKT conditions, so we have a solution. Okay, so if this math is maybe not making that much sense to you because it's lecture and it's always hard to look at kind of details in lecture, just look at the picture. And then you can go through the math on your own time and make sure it makes sense to you. So the picture says that we have a valid solution from 0 up until some point unless two paths cross. And when does that happen? That happens at some value of lambda that we determine. And because two paths don't cross the entire interval, then we know for sure that we've actually solved the KKT conditions because we've assumed in writing them down that we can have subgradients equal to what they were here. So they have to be on the same side of each other. Now at this point we do the same thing. We just say that unless two paths cross, we're going to define the solution in such a way that it solves the KKT conditions, assuming that they're on the right side of each other. So we move until two paths cross. And it looks like it's actually the red and the pink ones that cross. These are just very close to each other, so they probably will have crossed for only a slightly larger value of lambda. But it's actually this value of lambda which they cross. So the definition, how we seek that value of lambda out is the same as we did in the first case. We just set those two linear paths equal to each other for all I, and we find the minimum crossing time. And just from exactly what we've shown, the solution between lambda 1 and lambda 2 is exactly that. So it is indeed linear in between those two critical points. So we're just going to repeat this strategy until all the coordinates are fused into one big group. And then we know it's the end of the path. Because once they're into one group, they don't change groups from that lemma. Other questions about that? So this comes from, this algorithm comes from two observations. The first observation is that when things fuse, they don't unfuse. So probably what happened was somebody was playing around with the problem, and they were trying it for discrete lambdas with some solver, and they noticed this property. And said, oh, that's pretty cool, I should try to prove that. And that's what happened. Somebody came up with a lemma with that, and that's why that lemma is there. Then once you know that lemma, it essentially tells you that you can reduce the dimension of the problem by 1 at every critical value. Right? Because when two things fuse, I just have one less optimization variable, given that lemma. So it makes the problem easier. And then this path algorithm is actually very natural. It just tells you I'm going to move from fusion point to fusion point, reduce the dimension of the problem by 1 at each step, and it turns out that the solution is actually linear in between those two critical points. So the solution here is unique, right? Because this problem is strictly convex. Look at this problem. So actually this is the solution path. It's not a solution path, it's the solution path. So there's only one and it's piecewise linear and it has this exact behavior. So here's a summary of the algorithm. It's pretty simple, and even though it looks like there's a little bit of bookkeeping to do with the signs, I'm sure you could code this up in MATLAB or in R, no problem. You just start with lambda equals 0, the number of groups being equal to n, and every component being in its own group. And we start with the solution being equal to y at lambda equals 0. Then for every value of k, which is the number of fusions we have, we're going to compute the average of y within each group, basically, and the slope that we propose to move the solution along some linear direction, and this is the slope. And it just depends on the solution at the previous value of lambda. So we always know this. Right, at k equals 1, this depends on the solution at lambda equals 0, and that which is equal to y. And at every successive value of k, it depends on the solution at the previous critical point. So then we're going to say that the solution is exactly equal to ai minus lambda bi until lambda reaches the next critical value. And that's determined just by finding the smallest value of the differences of the ais of the differences of the bi's. That just comes from setting those two paths equal to each other and find the first time that happens. And then once we find that value of lambda, we merge the appropriate groups. Right? If these two end up being equal, we're going to say that I'm going to merge groups I and I plus 1. I'm going to decrease the number of groups, and I'll just go back and repeat it. Okay, so a very simple algorithm. And here's what the path looks like as a function of lambda. So I just was showing you a zoomed-in version of like the first bit of the path, but here's what the whole path looks like. We start off with all the components equal to y. We let lambda increase, and we study the evolution of the path until these two components cross, and then we say that's going to be one group from now on, and we repeat that strategy over and over again until everything's in one group. And this picture tells us exactly that when two of these lines cross, they're never going to uncross as lambda increases because of that lemma. Why is there crossing where? Oh, right here. So that's a good question. The question was why can these cross? And it's because these don't correspond to adjacent groups. So remember, the ordering here is to do with the y value, but it's nothing to do with where they are ordered along the line. So if we can probably figure that out from the picture, it might have been, yeah, it's hard to tell from the picture, but it could have been that, for example, the solution, what's that? Yeah, you're right. So at some point, as we let lambda evolve, these two values can be equal, but that doesn't correspond to fusion because they're not actually adjacent. There's a group separating them. That's a good question. It is the unique solution because this problem is strictly convex. Okay, so at every value of lambda there's only one solution. We found a solution, so it is the unique solution. Okay, so anytime you run something like a first order method or quarter descent or anything that we talked about, we're finding kind of one vertical stripe here. Right? We're finding one solution of lambda, which is like taking a cross section of this path. So it would have given us somewhere, and if we were lucky, we might have ended up exactly at a critical point. But since there's finally many critical points, if we're sampling lambda at random or something, that would never happen. So this actually gives us the whole solution path. So let's just quickly talk about computational complexity, and then we'll take a break and we'll get to more general problems. So how would you implement this? Well, naively, if we go back and look at this algorithm, every iteration takes order n operations, right? Because we're just scanning over G groups, but that's of order n. It's certainly of order n at the start. And there's order n iterations of the algorithm, right? Because at every iteration, we're going to merge two things. So there's actually n minus 1 iterations. So the total complexity is naively order n squared, which is actually already pretty good. Right? If I told you I could fit the entire solution path of this total variation denoising problem in order n squared, that's already pretty good. That can scale to fairly large problems. But actually, you can use a tree for the implementation, and you can reduce the computational complexity a lot. So now we can scale this algorithm up to being able to solve really large problems. So how do we do that? If you look at the equations I wrote down, you notice that after we fused two groups, the crossing times only changed for things that were adjacent to the components that were fused. Right? So for every, let's take a look, for example, at this blue and that pink path. Okay, so when I'm here, I've computed a crossing time for that blue and that pink path, say at this value of lambda. And it's this lambda up here at which they will cross. But before that, the red and the orange cross, before I could reach that crossing time. So now when the red and the orange cross, you can notice you don't have to actually recompute the crossing time for the blue and the pink. It's the same as it was before. It's because neither of those groups were adjacent to either the red or the orange group. So even though I computed at a previous lambda, it's still the valid crossing time. And you can see that from just studying the equations. Okay, so once I compute crossing times, they're valid for all larger values of lambda unless it's adjacent to one of the two things that were joined. So now we store the solution path in a tree. Okay, so every leaf of the tree corresponds to one component, and I just kind of I draw a parent of that leaf when they fuse at their crossing time. And if I ever have to update that, I can just go and update that value, but I won't have to update it. I only have to update a constant number of things at each fusion. Because at any level of the tree, all of those crossing times will be valid, unless you're a neighbor of the things that was just fused. So then at each point, I'm actually going to query the tree for the minimum, which is the next crossing time. And because it's a tree, I can keep these ordered, so I can do that in log n time. So now at every iteration, I'm going to keep the crossing times in the groups in a tree. I can update that tree in constant time because only a constant number of things change. And then querying the tree for the minimum is a log n operation. It requires log n operations. So now the total is actually n log n. Right? N iterations. Each iteration requires log n since we've stored it in this tree. And now this is a very, very fast algorithm for this problem that can scale to huge problems. Was there a question there? Yeah, that's a good point. So the question was, does log n comes if the tree's balanced? But I can use something like a red-black tree, which is a type of tree that's a self-balancing tree, and it'll always be log n. So, I mean, to really get, I guess, to get a very good implementation of this, you probably would use something like a red-black tree, and that's getting into some of the data structures, but you could still probably use just a regular tree in practice, and it would at least be close to n log n. Okay, so even naively, this path algorithm is pretty fast, and then, like we saw with coordinate descent, if we're careful about how we implement it, it can actually be state-of-the-art. Right, so n log n for the whole path is very good because now, if I wanted 100 solutions along the path, now it's just constant time because I've stored the path, and I can just query it for those 100 values. Okay, let's take a quick break, and then we'll get back to path algorithms for more general problems. Okay. So we're going to get to kind of generalizations of this in a second, both within the Fuse-Lasso problem and also outside of the Fuse-Lasso problem. But before that, I just wanted to kind of query you guys to see how many people that makes sense to, because it's a very, very simple concept, and if it doesn't make sense to some people, then I'd like to have you leave here saying they understood a path algorithm. Because I had some comments from some students earlier that this subject to them is very obtuse. Like when people see this in the literature, it's a very obtuse subject and it's hard to understand. So I was trying to give you a concrete example. Somebody still lost? I'm very happy to go over it again if people are still kind of a bit uncertain. Okay, well, I'll take that as a good sign rather than as a lack of wanting to say that you're lost. But you can ask me about it afterwards if you want. So just think about this example when you think about path algorithms. Right? We basically recognize some structure. We exploit that structure, and we write down a solution that's kind of been backwards engineered to satisfy the KKT conditions. So we successively satisfy them by writing down a solution that does, and then as soon as they break, we stop. We're not going to move any farther. That's when these paths would cross, and we kind of redefine the solution from that point on. So here's some extensions beyond the 1D case. If I have an arbitrary graph, so suppose I'm doing the Fuse-Lasso problem, or the total variation denoising problem, but instead of doing it on a line, I'm now solving this problem. Minimize yi minus xi squared plus lambda times the sum over all I and j that are edges with respect to some edge set over the components of xi minus xj. Okay, then surprisingly, at least to me, that lemma doesn't hold. So we still get the property that as we increase lambda, things fuse. So one component of the solution will fuse with another, and groups will fuse with other groups. But it can be the case that actually two things that were fused at some value of lambda unfuse as lambda increases. I find that counterintuitive because lambda is the penalty is the weight that we put on the penalty term, right? We're putting a penalty in this criterion for any difference between a component and its neighbor with respect to this graph. So if they are equal and we increase the weight in the penalty, you'd expect them to be equal still. But actually it can be the case that at the solution, they become unequal, or they unfuse. So given that key lemma doesn't hold, at every lambda we actually have to now check that we have to check for when two groups will fuse, the crossing times that we talked about in the 1D case. We also have to check for when groups that were fused will unfuse. And that latter check is actually a lot harder. Okay, so this paper that I wrote down, the reference for you can take a look at it. It actually does give you an exact path algorithm for the general graph case, which is very nice. So we can construct a piecewise linear path with critical values, just like before, for the case of an arbitrary graph. But every iteration now, instead of just being a log n check or an order n check, depending how you implement it, every iteration has been reduced to solving a single max flow problem on a graph that's kind of defined in terms of the graph that the current graph we're looking at. So now it's a lot more costly, right? We didn't talk about max flow, but you can probably remember from previous classes, it's a lot more than n or log n. Okay, so we've reduced the subproblem to something that's solvable, so we can actually do it in practice, but it's not this fast anymore. And because of the fact that this lemma doesn't hold, not only is each subproblem harder, but we actually have more subproblems. Right? So now there's not an order n bound on the number of steps in the algorithm. Things can fuse and unfuse many, many times. Another possibility, which I'm not going to cover in class, is that we could have derived the path algorithm for the dual problem. So we could have written down the dual of this problem here. And we could have actually derived a path algorithm for that. And then, arguably, it's actually a lot simpler in that case, because instead of reducing it to max flow problems, which, those are kind of a different subject and complicated, they're complicated to study, we can reduce every subproblem just to a linear system. Okay, so the complexity doesn't actually improve that much. It's about the same complexity, but maybe conceptually it's simpler had we done it from the dual. And just to mention that if we wanted to put an x in the loss, right? So in this case, we're just doing. Again, I'm being a statistician here, so I think I'm confusing everybody. So don't look at what I wrote in the slide. But right now, we're using this as the loss, y minus x squared. But we can actually stick a matrix of covariates in there, had we had covariates, and we can solve the problem for the regression loss as well. Okay, so extensions to that case are also possible. Yeah? Yeah, that's a good question. So it holds for the chain graph that I just drew you, and it also holds for the complete graph. And for the complete graph, there's actually a very simple algorithm also. I don't know if there is a broad class of graphs for which it holds. That's a good question. I can tell you that if D is the oriented instance matrix of the graph, so D is going to be the number of edges by the number of nodes, and in every row of the graph of this matrix I have a -1 and a 1 that corresponds to connecting those two nodes by an edge. This is called the oriented instance matrix. Incidence matrix. Then a sufficient condition for that lemma to hold, which is not necessary, because for example it doesn't hold for the complete graph, is that DD transpose is diagonally dominant. So that gives you one type of, or some types of graphs, but it's a pretty small class. And I probably couldn't enumerate for you very many graphs that lie in that class. The chain graph is one. That was a very good question. So how about more broadly, beyond just this fused-lasso class of problems? Well, so we can derive the exact path algorithms, and I gave you a bunch of references at the end in case you're interested, for the lasso problem, for the fused lasso problems over arbitrary graphs, for trend filtering, which we didn't really talk about, but it's kind of like doing piecewise polynomial estimation, for locally adaptive regression splines, which is again another kind of piecewise polynomial estimator. For SVMs and kernel SVMs, they're actually our exact path algorithms. So in this case, it describes the solution as the right? We have a parameter c on the slacks. Remember in the SVM loss? So this describes the solution as c evolves, as c increases. Same thing with kernel SVMs. For one-norm SVMs, we also didn't talk about that, but you can actually you can write the SVM as a penalized problem, just like in this form. We have the start, and you can replace h, which is a two-norm penalty squared, two-norm squared penalty in SVMs with a one-norm, and you get a very different flavor of SVM. That's called the one-norm SVM. We can also drive a path algorithm for that problem explicitly, and people have looked at path algorithms for these relaxed maximum entry problems as well. So there's a pretty big range of problems for which exact path algorithms exist. In all of these examples, they follow the same prescription as the one we talked about, which is that the solution is piecewise linear in lambda. Remember, lambda was the tuning parameter in this general problem. So the problem of computing the path reduces to finding a finite number of critical points. Just finds t points at which the solution changes. It's exactly linear in between those. There's actually another paper I gave you in the end that gives you sufficient conditions for when this is true for a general problem. So it tells you if you have a problem of the form f plus g, it gives you sufficient conditions under which the solution will be piecewise linear with respect to lambda, so that you might have even the hope of driving a path algorithm to begin with. So what are some of the drawbacks of using path algorithms, or some of the kind of shortcomings in at least our study of path algorithms? For the majority of the examples I listed, for pretty much everything except for that chain problem for the one diffuse lasso and a couple other special cases, we don't know tight bounds for the number of critical values t. So we can't get tight running times for the algorithms. I'm sorry? Even for lasso, yeah. We don't know. So for the lasso, each value of lambda corresponds to a variable that has become non-zero at the solution. Right, so for this problem, for the one diffuse lasso, the t is bounded by n minus 1. Yeah. So I think the things don't fuse with the lasso, but this might be an example solution path for the lasso that we see. So here's 0, and this is actually corresponds to lambda equals infinity, where they're all 0. And as I move this way, I'm going to lambda equals 0. Okay, so that parameterization is maybe a little bit funny because I have infinity at a specific spot on the axis, but I can also parameterize it by like the bound form or something, if that bothers you. So what happens is as we decrease lambda a bit, things become non-zero, right? But what can happen with the lasso, which is the analogy to things unfusing, is that things that were non-zero can actually become 0 again. It happens all the time. It happens for almost every design matrix except for a very restricted class. So just like I told you that for the fuse lasso, we can prove that it doesn't happen if DD transpose is diagonally dominant. There's another condition on A, which I'm probably going to get wrong, but it looks something like A pseudo-inverse times A pseudo-inverse transpose is diagonally dominant. Or it's something like that, with the transposes maybe mixed up. So very, very few design matrices satisfy this. If you go and you just have a problem, you'll see that almost all the time they come back to 0 at some point. So that was a good question. But yeah, for all these problems, we don't know how to bound, with a tight bound, the number of critical values. So it's hard to say for any given problem whether it's going to take a long time or a little time. And a very loose bound for the number of critical values is exponential. We can say the number of critical values is something like less than 3 to the n. But that's not very helpful for any purpose. Question, yeah? So in all these problems, critical value means a value of lambda at which the solution changes in terms of the piecewise linear structure. So all these examples are piecewise linear with respect to lambda. So critical value is just a value of lambda at which, one of the kinks of that piecewise linear path. Yeah. No, that's a good question. So if I took this problem, which is the lasso problem, and instead of writing down the 1 norm, I wrote down a 2 norm squared, then the solution path here is actually not piecewise linear anymore. So this is ridge regression. The solution path is not piecewise linear, it's actually curved. But we can write down what it is explicitly as a function of lambda. It's even easier than lasso because the solution is equal to A transpose A plus lambda I inverse A transpose Y. So that's actually an explicit formula for the solution as a function of lambda. And if you draw these paths, you'll see they actually are curved. This kind of applies a shrinkage to the singular vectors of, or to the right and left singular vectors of A. If you write this out in terms of the SVD, you can see kind of how it acts on the singular vectors. And they lead to curved paths, but in a sense it's easier because we actually know the explicit solution. So if I just throw down an arbitrary f and g, I might not get a piecewise linear path, so critical value doesn't make much sense. But I'm just talking about the cases in which they are piecewise linear. And that's true for all of these problems. So a very broad class of problems that we're interested in. Good questions. Yeah, so we're actually kind of shorter on time than I thought we would be. I'm going to kind of briefly give a use of path algorithms for the statistical problem that I had mentioned at the start. I hoped I would have a little more time to discuss this, but we'll use what time we have. So broadly, these path algorithms trace out the solution as a function of the tuning parameter, lambda, right? So they're completely describing the trade-off between f and g. They're not telling us for one value of lambda what the trade-off is. They're telling us how the solution behaves as we actually turn the knob for that trade-off. So they often aid in kind of a statistical understanding or even choice of lambda in a statistical context. So for this fused lasso problem, if I didn't choose lambda appropriately, I would have been in a lot of trouble. Right? For lambda too small, I get way too jagged of a solution. For lambda too big, I'm missing the structure completely, or at least I'm doing very poor estimation. For lambda somewhere in the middle, I have a decent estimate of the underlying trend. So how did I choose this? I chose this by eye, and obviously that's not really possible in most applications, or it's not a very principled way of choosing lambda. So a big kind of part of statistical learning is concerned with choosing these tuning parameters automatically. And when we solve the problem using a path algorithm, that provides us a platform for how to do so. So I wanted to describe that in the remaining time we have. So I'm going to skip all of the statistical motivation which I wrote down, and please go through and look through it if you're interested in it. But here's the punchline. If I observe some y, after I make some assumptions that I skipped over, I can form an unbiased estimate for the prediction error of my estimator as a function of lambda by taking the training error. This is how well y fit to y hat here is the solution. I'm calling it y hat because in statistics we often use that notation to reflect an estimator. So this is the training error. It's how well I did in terms of fitting the data that I was given, plus 2 times something. This is like the variance of the noise term, times this, which is an unbiased estimator for the degrees of freedom of the estimator. So this term, like I said, is training error. This term is degrees of freedom. This reflects model complexity. So the more complex the model I'm fitting, the higher the degrees of freedom. So if I'm in the overfitting regime, the training error is the training error is small, right? So if I go back to this picture, I have very small training error. I'm very close to the points, but model complexity is very high. So you'd expect that the degrees of freedom term would reflect that. If I'm in the underfitting regime, which is like this last picture here, the training error is, the degrees of freedom is very low. Right here I've fit not a very complex model, but the training error is pretty bad. Okay, so when I form this unbiased estimate of prediction error, it's a balance between model complexity and adaptivity in the sample. So you might think that you could choose lambda in order to minimize this, because it exactly balances the trade-off between kind of the two regimes, underfitting and overfitting, that we don't want to be in. And path algorithms actually provide us with a way to do this. Yeah? Degrees of freedom. The exact definition for degrees of freedom is here. And just because I have like 2 minutes left, I don't think I can really go over this. But take a look at this. It basically tells you that the more that the more influence a point has on its fitted value, the higher the degrees of freedom. Right? So y hat's a function of y. If the covariance between y hat I and yi is very high, that means that y had a lot of influence on its fitted values. So the higher that covariance, the higher the degrees of freedom. So how do path algorithms fit in here? Again, I have to be pretty broad, but because they trace out the exact solution path, it's often actually easier to compute these degrees of freedom values as lambda varies using a path algorithm. And in many cases, this presents no extra work. A lot of times those degrees of freedom estimates, they come exactly from the path algorithm manipulations, from the computations. So that's good. So now we have an estimate for degrees of freedom. But then we have to also choose lambda, right? Lambda was going to be chosen to minimize this estimate of prediction error, which is a non-convex problem. So that's pretty difficult in general. And it's non-convex because I didn't tell you how this behaves as a function of lambda, but this is not convex. And it actually can also happen that this is non-convex as a function of lambda as well. So in many of the examples that I presented to you, in fact, all of the ones that I wrote down, our degrees of freedom estimate is piecewise constant with respect to lambda, which means it's actually just one value, and it only changes when we hit a critical value. So this term is the same in between critical values. And you can also prove that in very general terms, this is monotone in between critical values. So it's a monotone function between critical values. That means that this can only be minimized at a critical value, because in between critical values it's just monotone. So I've reduced a non-convex problem to now minimizing for lambda over a discrete set. And that discrete set is exactly the critical values that are visited by the algorithm. So by using a path algorithm, I can just, along the way that I'm tracing out the solution, I can just evaluate this at every critical value that I visited, and it'll give me an estimate of this prediction error. So here's just a simple example. I did that for this problem. This was what that prediction error curve looked like. It's in black. I also decomposed it into the two components so you could see what was going on. This red component is the training error term. So when lambda is small, it's very small. We have great training error. And as lambda gets larger, it gets worse and worse. And this green component here is the degrees of freedom term. So when lambda is small, we have high model complexity, right? A lot of jaggedness. And then as lambda increases, it gets smaller and smaller. And when I add the two of them together, I get this black curve. And to choose lambda, I'm proposing, let's just find the spot on the curve, the value of lambda that minimizes this curve. And that was this blue point. Okay, and at that blue point, here's the solution. So now we've used a path algorithm. It's found us the entire path of solutions, and it's also chosen one for us automatically. And this is the solution that it shows. You can see it's still probably not ideal. There's still probably a little bit too much adaptivity here in this region, but it's pretty good. It's certainly good with respect to other solutions along the path. Yeah, question? Multiple testing.
Like, because you're optimizing over different models. Like, this is like the model, you're doing algorithmic model selection. Right? And in model selection, then you would also add not only just like a complexity penalty, but there are multiple testing penalties.
Yeah, I mean, so.
People just use this directly to get lambda?
So there's not really a consensus as to what to use. It's a very. There's kind of a bunch of theory for this problem for cases in which we don't care about. So you can take that theory and you can kind of argue for various that it's going to hold in various applications, but the truth is that there's no theory for problems we care about. So I think maybe what you're talking about is that you have to kind of put more weight on this term because of the fact that you're minimizing over many values of lambda. So this is called SURE, Stein's unbiased risk estimate. This is what this is called. If I replace this 2 by a log n, then that becomes something that's kind of like BIC, and there's people who would argue that's better. And if you change it to something else, there's people who would argue that's better as well. But to be honest, there's not like a unified theory for why any one of these particular methods works for problems that we care about. That's a good question. Compare this with cross-validation? Yeah, a good question. So you can also choose lambda by cross-validation. This is a different, a completely different strategy. There's not, well, yeah, so yes, there is a theory which connects something like this to cross-validation, but again, it's for a class of problems that are very simple. It's for a bunch of linear regression problems in which the number of variables is fixed and the number of observations goes to infinity. So in that case, you can show that actually this kind of, in a sense, asymptotically approaches cross-validation. If I do linear regression on a fixed number of variables and let the number of observations go to infinity, then this is doing what validation would do. But aside from that case, it's hard to know the comparisons. Again, some broad comparisons are this is a lot cheaper computationally because I'm not refitting this cross-validation. I have to refine the solution on a bunch of folds. But also in deriving this, I've actually placed a lot more assumptions than I have in using cross-validation. I didn't show you what the assumptions were, but they looked like this. I believe that I had kind of independent errors with the same variance and zero mean. Cross-validation doesn't assume a model for the data. It just assumes basically that the observations that I have are independent, but no error model, nothing like the common variance, nothing like that. Or it really all assumes its exchangeability between the observations. So that's a good question also. All right, that's I guess all we have for today. Make sure to come next week. We have some good advanced topic lectures.